So in this video, what I'm going to do is go ahead and go over the proof for finding the derivative of inverse sine. We're going to generate a formula. Once that formula is generated, we're going to practice using it over and over in different scenarios in class. But this is sort of the proof, and you can use this to fill out your blue paper. The first thing I'm going to do is give you a little bit of side knowledge that we need to know. Back in trigonometry, you learned that the cosine squared of some theta or x or whatever, I'm just going to put a star for now because I want you to understand that really anything could be here. Any variable could be used. Plus sine squared of star, if you ever had that, the result would be 1. That's an identity that it's one of the basic ones that you probably learned in pre-calc. Well, this is not a static equation. It can be changed. For example, I can easily solve for cosine by simply subtracting sine squared from both sides, so that cosine squared of star, remember I'm using star because I want you to realize that any variable could really be here. Could be x, could be theta, could be y, could be anything. I subtract that sine squared from both sides, star, and then because I have a squared, I will take the square root of both sides, and any time that you take a square root, that is going to cause a plus or minus. So cosine of star will equal plus or minus the square root of 1 minus sine squared of star. Now, we still haven't started the proof. I'm just kind of doing this on the side because we're going to come back to this concept later. It's going to be something that's going to come up in the proof. Alright, so just keep that in mind. Now we're going to go back to inverse sine, and I know that you guys don't have that much experience with this, but here is the graph. And what I'm going to try to do with this inverse sine is write it so that this notation of inverse isn't there. I'm going to try to write it, so that the notation only has a sign in it. And because it's an inverse sine, I know from inverse functions that if I take the sine of inverse sine, that will cancel, leaving me with x. But I can't just do that to the right side. I have to do it to both sides. And by the way, that is a property of functions. If you take a function and you insert the inverse of it inside, the result will be x. Okay, and it's the same thing if you go backwards. If you go the original into its inverse, the result will be x. In fact, back in pre-calc or even math analysis, you were probably asked to check if functions were inverses by plugging them into each other and checking if the result was x. So we're going to kind of use that concept here, and we're going to take the sine of both sides. So here we are, the sine of y equal to the sine of the inverse sine of x. Okay? And so what that does essentially is these cancel out, leaving you with x. So you have sine of y equal to x. Okay? Well, we want to go ahead and solve for, we want to take the derivative. I want to go ahead and mention that this inverse sine and this notation that we just came up with, they're the same thing. This is the inverse right now. If you think about it, if the original function was y equals sine of x, if you switch the variables, you get this setup here. So really this guy and this guy are the same thing. This is just written with inverse notation, and this one is not solved for y. So we're going to go ahead and take the derivative in terms of x of this sine y equal to x, but because it's not solved for y, we're going to need implicit differentiation. So the derivative of sine, the outside, is cosine, leaving the inside alone, times the derivative of the inside, which is dy dx, or 1 times dy dx. On the right side, the derivative of x is 1, and I'm going to go ahead and solve for dy dx by dividing both sides by this cosine, leaving me with dy dx is going to equal 1 over the cosine of y. Now, this is technically the derivative of the inverse function, but it's currently in terms of y, and we would like to have a formula in terms of x, so we need to figure something out. I know that x equals sine of y. X does not equal cosine of y. But earlier in this yellow stuff I wrote over here, I saw that cosine of something equals plus or minus the square root of 1 minus sine squared of that something. So if I replace the star with y's, it kind of fits the problem I'm dealing with right now. Cosine of y is equal to the plus or minus square root of 1 minus sine squared of y. Now, we have to choose a plus or a minus. So if we look at the graph, you can see that you're always going to get a positive slope, which means your derivative should be positive. So instead of selecting the negative, we are going to select the positive. So we're replacing cosine with 1 over the positive square root of 1 minus sine squared of y. Okay? So we're still in terms of y. So why did we do this? Well, because we know that sine of y is equal to x. So you can see how this is going to become, sorry, let me switch my color here. You can see how this is going to become 1 over the square root of 1 minus, instead of sine squared, it's going to become x. And it's squared, so it becomes x squared. And this is the derivative that you have to memorize. The derivative of the sine of x is 1 over the square root of 1 minus x squared. So is this what you write in your blue sheet? Kind of. This is the proof of the derivative for sine of x. But what if this were 2x or x squared or 7x plus 3? Then it would be a composite. So in your blue sheet on that, kind of right below the graph on the row that's a little bit thinner than the other, you're going to write, in general, d dx, which means take the derivative of inverse sine of u. And so the reason we're using u represents some function. Again, that could be 3x, 4x, 5x squared, 2x squared plus 5x. U could really just be anything that you put inside a sine. The derivative of that is always going to be 1 over the square root of 1 minus whatever that u is squared, but because it will be a composite, you got to multiply by the derivative of u in terms of x. Chain rule, basically. So that's what goes in that middle piece, middle row of the paper. So, all right, then what does that mean for us in terms of taking derivative? I'm going to show you a very, very simple example, but this is what we're going to practice in class, okay? So inverse sine, let's say that we had y equal to sine of 3x. Sorry, inverse sine. Well, we need to use our formula because it's inverse sine, so the derivative of the inverse sine is going to be 1 over, and remember, y prime and dy dx are the same thing. 1 over the square root of 1 minus u. U is everything that's inside of the inverse side. So it's going to be 3x. Common mistake is only to square the x. You need to square the entire term. Okay? And then you need to multiply by the derivative of the inside, which in this case is 3. So as a multiple choice problem, you will not see it like this. This is a good setup. If this was free response, I would give you full credit. But if it's multiple choice, you need to see a 3 over the square root of 1 minus 3 times 3, 9, x times x, x squared, and this is your answer. So there's, a lot of times students kind of struggle with this general notation. Please just understand that this is just in case that inside of the sine is not simply x. If there's something else going on, you got to make sure you write down everything that's inside and then multiply by the derivative of the inside. And that's it. You're done.